You said that the older stars should be expected to have less of the helium, but wouldn't they accumulate more of it as they were fusing hydrogen?
No, because this is um, this is part of uh, the correct predictions when I and others looked at what would happen in the evolution of a galaxy, guided by what we knew of plasma physics and gravitation and nuclear fusion. So basically, what the prediction was that the size of stars that are produced at a given epoch in the galaxy's evolution was inversely correlated with the density of plasma that they came at. So you have bigger stars forming first. Bigger stars, everybody agrees, burn their uh, fuel much faster. It goes approximately as the cube, uh, inverse cube of the mass.
I see. So when you're talking about the age of stars, you're talking about whether it's a first or second or third generation star. You're talking about in the age of the galaxy.
I'm saying older stars are the ones that are produced earlier in the history of the galaxy and survive to the. They have to survive to today for us to observe them. But in the history of a galaxy, the first stars are the ones that are today the oldest. Well, those first stars, the stars that are even older than the ones that we see surviving, which did not survive, those were bigger and produced helium more rapidly. So that helium was incorporated into the later stars,
Got it.
which also did not survive until you get to approximately the third or fourth generation, in which the stars are small enough to have long enough lives. So the helium that we observe in their outer atmospheres is the helium that they acquired that was produced in earlier generations of stars. We can't, the helium that is in their core is, that's a separate, that we can measure separately, indirectly by how they vibrate. So we're talking about stars that in the outside, in their outer atmospheres, have much less than 24% helium. And the older the stars are, the earlier they were produced in this epoch when the stars were old and small enough to survive to the present day, then we see the helium go down. And all of these observations have been verified long after the predictions were made. Even before JWST, we saw that the younger galaxies had, on average, much bigger stars, and their ratio of luminosity to mass was hundreds of times larger. So that means absolutely they were producing helium hundreds of times faster than the Milky Way is today. That's a universal observation of galaxies. So, you know, helium is wrong, lithium is wrong. Deuterium, at the moment, they've got it right, but even some observations are saying maybe that's a little off. But deuterium is the only one they've got right. So, number three, me and my colleagues, Ricardo Scarpa and Renato Falomo, have concentrated for years on this Coleman test. You have an expanding universe, you have a strange optical illusion that objects at a far distance should look larger on the sky than nearer ones. This operates basically beyond the redshift of approximately 1. In a non-expanding universe, just like on Earth, obviously more distant objects get smaller in proportion to their distance, their diameter on the sky. We've done studies with HST, with JWST. We're about to publish a new one. There's an absolute 100% correspondence between the predictions of the non-expanding universe and observations of the images of galaxies. Absolute contradiction with the predictions of the Big Bang. And even though the Big Bangers who knew of these contradictions said, well, the galaxies were really small back then, so it compensates for the fact that they're not as large as we predict. Subsequent observations have shown that's physically impossible. There are independent measurements of the mass of galaxies that can be made two ways. Based on their luminosity, you can measure the amount of gas. And based on their velocity of rotation, which can be measured from their spectrum, you can use Newton's equations to measure their mass given their true linear radius. So the true linear radius in the Big Bang hypothesis is much smaller. You have these supermassive galaxies, galaxies as massive as our own, that are squeezed into 100 times smaller radius, 1,000,000 times smaller volume. But these observations completely cut through that because they show that the mass of gas is 10 or 20 or even 100 times bigger than the total mass of the galaxies if you use the Big Bang formula. And this contradiction completely disappears if you use the non-expanding formula. So you get what people call impossible galaxies.
Our video has come out of LPPFusion's research in fusion energy, the energy which will power a future of abundance for all, with a sustainable economy and a clean environment. Goods, housing, and transportation will be affordable to all once fusion kicks in. Fusion energy is the key to building a better world now. Support fusion research, $10 a month at lppfusion.com/support. The link is in the description. Thanks.